Can you maybe tell me how? Because I can't see anything like that here. I can only see share my tab. I can't see share. Please, can someone show me, like assist me in, I want to share my iPad screen, but I can't, I'm not seeing how.
Have you tried joining the call with your iPad?
Okay, let me do that.
I can just put a link in the chat section.
Oh, okay, that makes sense. Okay, perfect. Perfect. Yeah. Okay, you can see my screen, right? The iPad screen.
Yes, it's clear.
And can hear me properly.
Yes.
Nice, nice, nice. Perfect. So we have about 30 minutes. So let's see how far we can go. So basically, I'm going to take you step by step from some very basic concepts down to elliptical cryptography. Now, one thing I've learned is that these concepts are hard generally, right? But I feel like if you want to rephrase, they are just chaotic, right? And the way to handle things like this is that you try to manage chaos by breaking them down. That's how I try to learn these concepts, and I believe it's a helpful way to learn them, right? So what I did is I broke them down from what you'd likely understand, and we actually build up to what might be a bit harder, right? So just follow me and ask questions along the way, and I'll do my best to answer. And if you at any point, if you want clarification, you can just. So basically, we start with modular arithmetic, right? Or we can call it clock arithmetic, right? So basically, if you look at the diagram in front, it's more like just a clock, right? So let's say you have like the way our clocks work, 0, 1 to 11, right? Then when the clock moves around on the next um, on the next rotation, it's so if you have 13 o'clock is one, right? Because you are wrapping around the 12 values, right? 12 o'clock most times is represented as zero, right? So even if you have 22 o'clock, right, it's still 10, right? Because you are wrapping around 12 values, right? So that's how modular arithmetic works, right? That one I'm using a clock. It's called clock arithmetic, or it's mostly called modular arithmetic in most cases, right? So, but using a clock, you bet you understand it better. So let me just give an example. So 8 mod 12, right, is 8, right? So basically 8 in a clock is 8, right? 9 in a clock is 9, right? But 13 in a clock is 1, right? Because it wraps around ones and then you get 1, right? 30 is 6, because once you wrap once, you wrap twice, you have 24. then 30 minus 24, you have 6, right? Because now you've wrapped around the clock twice, right? So that's how modular arithmetic works. And lastly, you have 12 more 12 is 0, right? Because you are wrapping around once, and you have, if you have the same value as the modulus, so 12 in this case is the modulus, right? So you have 0, right? So let's quickly go through the Diffie-Hellman key exchange protocol. Now we're trying to solve a problem, which is how do Alice and Bob agree on a secret key in an adversarial environment like the internet, right? Which is the world we live in today. Which is, how do you and I share keys when, like, imagine we had a setting where every single person was on this call, and I needed to share key with, let's say, Michael, right? And how do we make sure that we share these keys while everybody is watching, but you can't still get the key we finally come up with, right? So this is the problem we're trying to solve. Now, how do we solve this problem? Now, I'll walk you through a set of steps. This is an algorithm, the Herman key protocol, and we'll work on it an example so you understand. Now, we choose a prime n, right? Which in this case might be, it doesn't necessarily have to be a prime in this case, but in most cases, in fact, in every most secure protocols always use um, the modulus as a prime, because there are benefits to having the modulus as a prime. Things like it has a modulo inverse, right? Things like that, right? So, sorry, a multiplicative inverse. You don't have to bother about that, but yeah, that's just one of the benefits of having a prime as your modulus, right? So this value now is this n is the modulus, which is similar to 12, right? It's like you can liken it to 12, but in this case, it's in our algorithm. So just see n as something like 12 or any other value you decide to use, right? And then we have a generator, which is a value that we want to start with. You can call a generator a starting point, a base point, right? And the generator will also use something like that in elliptic called Diffie-Hellman, right? Which is the starting value, right? And n and g are public. So when we do the work example, I will share the n and g for everybody to see, right? But then when we go through this protocol step by step, you understand that you know n, you know g, but you can't really find out the value we come up with, right? And then we share publicly. Alice generates a private key, right? Let's say you generate any value. Bob generates his own private key, right? As the name implies, private key, right? Then he computes G, which is generator, raised to power his private key modulo n, which is basically G. Let's say G is 2 and his private key is 3, which is 2 raised to power 3 mod. Let's say the n is 7 mod 7, right? And sends that value to Bob, right? So you all are seeing that the value passing, but you don't really know what it is because you can't really find A. You can try to find G raised to power A combined, which is 2 raised to power 3. You can find 8 modulo 7, but you can't know exactly the exact value I raised 2 to the power to get 8. You understand? And you would in most cases you actually use really large values, really large values. Like if you have a very small key size, it's easily broken, right? But in this case, you have, like I said, G raised to power A and mod n, and the same thing for Bob. Bob does G raised to power B, which is his own private key, right? Mod n, and sends it to Alice. Now, the interesting part is that now what Alice needs to do is that she takes the value sent by Bob and squares it, like raises it to a private key again, modulo n. So let's just do it so that it doesn't seem vague. So let's just quickly do this. Alice and Bob. We have, let's call this person at the middle Eve. This is a very popular name for explaining an adversary in cryptography. So you have Alice, you have Bob, and then you have Eve. Eve is the person in the middle trying to steal our value, right? So let's say n is 7. I'm putting it in the middle because everybody knows it, right? So basically, if the adversary knows that value, that means we also know it. That's why it's in the middle. So everybody knows n, and Let's say we also have G. Let's say G is 2. Now I'm using small values here so that I'll be able to compute them fast. In most cases, you use really large values that's impossible to compute without using a calculator. So now let's say Alice chooses a private key A equals to 3, and Bob chooses a private key B equals to I need a small value so I don't get stuck. Let's say 5. Hopefully able to compute that. So basically, so as the protocol says, um Alice computes G raised to power A mod n. So basically G is 2. So G raised to power A mod n, which in this case is G is 2, G is 2, A is 3 mod 7, right? So 8 is then mod 7. 8 mod 7 is 1, right? So just the way 13 mod 12 is 1 in the clock, right? So we let's call this value f. So f is equals to 1, right? And Bob does the same thing. Bob does G raised to power B mod n, right? G is 2, B is 5 mod n, right? 2 raised to power 5 is 32. 32 mod 7 is 4. So 32 mod 7 is 4. So we have um, h equals to 4 and f equals to 1. Now, like the protocol says, Alice sends f to Bob and Bob sends h to Alice. So they exchange their values, right? So let's say send h here. So we send f here and you send h here. Oh, sorry. Yeah, you you send h here. Yeah. So now what Alice does is that now she has Bob has f and Alice has h, right? Now what Alice does is she takes h and does h raised to power a mod n, right? And the same thing for Bob does f raised to power b, which is his own private key, right? So they know their private key, they don't know the other person's private key, but they make computations on the other person's private value that they generated by themselves, right? So f mod n. Now let's quickly compute this. H is 4. 4 raised to power a is 3 mod 7, and f is 1, right? F is 1. F mod raised to power b mod n. So you have 1 raised to power 5, right? 1 raised to power 5 mod 7. Now 4 raised to power 3 is mm, 4 3. 4 raised to power 3, 4 times 4, 16, 16 times 4, 64. So 64 mod 7. I think this is getting a bit funky, so just take this up a bit. So 64 mod 7 and 1 mod 7, right? 64 mod 7 is 1 because 63 7 times 9 is 63. So if you do 64 minus 63, you get 1, right? So 64 mod 7 is 1 and 1 mod 7 is 1. Now because we're getting one, it seems like the value is easy to compute. But now they've been able to come up with the same value, which is 1 and 1, without actually telling each other their private keys, right? And if you go a bit deeper, you now understand that what actually happened here is let's clean. um, okay, so now what actually happened here is that because of Alice did G raised to power A mod n and sent it to Bob. Bob basically did this value raised to power b. So if you see what happened here, it's basically they are making computations on secret values without knowing what is inside, right? The same thing for Bob. What actually happened was Bob did this raised to power b mod n, then Alice placed her own value on top, which makes it same value because g raised to power ab is always the same value, right? So this is the why this actually works, because at the end they arrive at the same value, right? Because you are sharing values, but you are hiding those values, right? So let's quickly move on. Now, a concept that people kind of shy away from, but it's very important, is groups, right? Groups is a concept on its own. Like on its own, it doesn't use elliptic cryptography or cryptography, but concept uses it, because basically what groups does is that it's a generalization that can be applied in many fields. So you have to understand this, because most of the concepts you'll be hearing when you're reading about elliptic cryptography, like finite field, group operations, and things like that. And if you don't know it, you don't know it, right? So like I said, I like breaking this thing down into different concepts, right? So after understanding all this concept, likewise, I'm not optimizing on finishing this today. I'm optimizing on trying to explain the fundamentals as much as possible. You understand? So that one dealing with this concept, because I believe if you understand this concept, if you see a bigger concept, you understand them better, right? So the concept of groups falls under abstract algebra, which is a very interesting field of mathematics. It seems very hard from the outside, but when you go inside, you just find out that it's a generalization of different things that you normally use in different parts of mathematics, right? So basically, a group is denoted by this. You don't have to worry about that. It's a set where some operations satisfies basically what I mean by CAIN is like closure, associativity, identity, and inverse, right? So let's quickly explain that, right? So um, let's say a group of integers under the addition operation, right? So like I said, a group is denoted by this. It's a set under some operations, right? If it satisfies these following things, right? So what what I'm going to do is that I'm going to give you a set, and I'm going to apply these operations. I'm going to apply these operations on them, right? To show that they actually hold, right? So let's check the set of integers. So the set of integers basically let's say -5, -4. Okay, no, it's infinity. So let's just do something like this: -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, blah blah blah, infinity, right? So this is a set of integers, right? Um, 1, -1, and so on and so forth, right? Now, the first thing we do is that we check closure. What's the meaning of closure? Closure is that if you apply the operation addition on two values, would these results still be in this set, right? So let's pick two values randomly. Let's pick -1 and 1, right? So let's say let's talk about closure. Let's pick two values randomly. -1 plus 1 is equal to 0. 0 is part of the set, right? Let's pick 4 and 5, right? 4 and 5, 9. 9 is part of it. I said infinity, but there are more values than 9 is part of it, right? Let's pick -4 and -4 and 4, 0, right? So basically closure holds, right? So for the sake of space, let's just remove this. This is operation is closed under addition, right? Addition of integers, right? So let's see associativity. So basically, what associativity means is that if I say um, -2 plus 2, let's say 3 minus 3, right? If I should shuffle this a bit and say, like, okay, this is equals to um, bracket. So using board mass, we first do the bracket. So 3 minus 3 is 0, right? And then -2 plus 0 is -2, right? But then if I should change this a bit to -2 plus 3, okay, -2 plus 3 minus 3, right? Which is basically changing the formation and like shifting some values, right? Does the addition operation still hold, right? Okay, no. Let me change this to addition. Yeah, because it's the operation, we are using the addition operation here. So, right, so 3 plus 3, 6 plus -2, right? Which is -2 plus 6 is 4, right? So, yeah, so if we change this a bit and do -2 plus 3, right, then this value, let's see, do we come up with the same value, right? So -2 plus 3 is 1, right? So 1 plus 3 is still 4, right? So this is what associativity means, which is if you change the ordering, right, does this actually still hold, right? And you can quickly think about something like division. Division doesn't hold. If I say 5 divided by 2 divided by 3 and change this to 3 divided by 5, blah, 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 it doesn't hold, right? So, but the operation negative, sorry, can you rephrase? Basically, is the operation we are focusing on, not necessarily the sign in front of the values, right? So basically, addition operation holds, right? But um, subtraction doesn't hold, because if I'm supposed to add to a value and subtract from it, right, then automatically, um, okay, that's not actually true, because subtraction is like reverse addition, but we're focusing on addition now. So let's just, so associativity holds. So let me just quickly tag that as true. Then let's see another one, which is identity. So what identity means is that, can you find a value in that set that when operated upon, you get the same value? And the most obvious value, or the only identity you have here, is 0, because anything plus 0 is 0, right? Anything plus 0 is 0. Even if you do subtraction, anything minus 0 is 0. So the identity element is involved in this set, right? Which is this 0. That means it actually holds, right? So basically, identity works, right? So lastly, which is the inverse, right? The inverse is basically which value in that set would I operate upon to get 0. That's what inverse means, right? So basically, you can say that the inverse of 1, right? So let's do inverse. The inverse of 1 is -1. The inverse of 2 is -2, because basically, if I do 1 plus -1, which is basically 1 minus 1, you get 0. If I do 2 plus -2, which is basically 2 minus 2, you get 0, right? So basically, in this set, we have these values, right? So now let's see another example that is not a group, right? That is not a group, which is the set of integers without 0, right? So we are a bit short of time. So basically, what I'll do is I'll just run it through quickly. So now you have the integers without 0. Closure holds, right? Because if you pick two values and add it, right? Two random values, you are likely to get the value, except that value is 0. But then let's leave that a bit. So let's say we pick two, we pick -2 and 3, right? -2 plus 3 is 1. 1 is in that set, right? So let's just say identity holds, right? It's not in all cases, but let's just say identity holds because we'll still find a clear indication that this is not a group. So let's just pardon that one a bit, right? So associativity, let's just say it also holds, right? Because it's only 0 that we don't have, right? So let's just say associativity holds. All right. Then the most important, and which is I wrote identity here. Sorry. So identity doesn't hold because 0 is supposed to be the identity, right? But it doesn't hold, right? So this is not a group, right? So the set of integers without 0 is not a group, right? It's actually not a group, right? So and basically we'll quickly talk about a cyclic group. Um, Yeah, but what a cyclic group means is that it's a group, but with an extra feature, which is that it contains an element called a generator element. And what's a generator element? Remember we talked about generator in the Behelman. So generator is a value that you can use to generate other values, right? Or you can use to generate all values in a set, right? So let me just quickly use this as an instance. You have this set of values, right? And it works it works like it works in modular arithmetic. So if you get, let's say, um w raised to power 3 as we actually got here, you would reverse to 1, right? So basically it works like you're doing modular arithmetic, right? So basically, let's find the generator, right? So basically, we have 1, we have 3. Sorry, we have 1, we have w, and we have w squared, right? So basically, we are trying to see if this group is a cyclic group, right? So basically, what's a cyclic group, right? Basically, is a group where you can use one element to generate other elements in the group or in the set, basically, right? So let's use this set for instance, and like I said, it contains only 3 elements and it works like it works in modular arithmetic. So when we get to w raised to power 3, we switch back to 0, we go back to 0, and it's more like when we just keep going around the circle, right? So let's see if, for solution, um let's see if this is a cyclic group, right? So we test with 1. So this is the set, right? So let's see if it's a cyclic group. So let's use 1 for instance. 1 raised to power 1 is 1, right? 1 raised to power 2 is 1. 1 raised to power 3 is 1. 1 raised to power 4 is 1. So this is not the generator element, right? Because we only tested one element, we cannot just say it is not a cyclic group. We have to test all elements to make sure, because if we check everything and we can't find one element that we can use to generate other elements in that set, then it is not a cyclic group, but would actually find out that later. So let's pick W. Now, W raised to power 1 is W, right? W raised to power 2 is W squared, right? And W raised to power 3 is 1. Like we said here, it works like modular arithmetic. So when we get 3, we switch back to 1. When we get 4 is W2, and so on and so forth, right? So W4 is equals to W2. I don't know if you guys are following, but basically it is wrapping around, right? It is wrapping around, right? So yeah, then that means W is a generator element, right? So please, if there's anything you don't understand, just ask in the chat. We'll definitely not be able to finish this today, but at least I believe I want us to be able to get at least the one we are talking about today, right? So W is a generator element. So let's see if W squared is also a generator element, right? W square. W square raised to power 1 is W square. W square raised to power 2 is W W raised to power 4, which is equals to um like I said, is equals to, okay, it's equals to W, not W square, sorry. So it's equals to W. because W cube is 1, so W squared, W, I don't know what it's called, but W raised to power 4 is W, right? So, right, so let's see, W raised to power 3, W2 raised to power 3 is equals to W raised to power 6. So, I think this is equals to, is equals to 3 or 2. Mm. So if W4 is W, then W5 is W square, then W6 is 1, right? W6 is 1, right? So let's check whether W raised to power 4 is still, so it is W raised to power 8, right? So if W raised to power 6, oh, we don't even need to go further. We've actually gotten the three element. I actually thought we've not gotten it, right? So we've gotten one W and W2, right? Which is basically the three element, right? So W2 is a generator element, right? So basically, this is a cyclic group. So why are we even talking about cyclic group? Because the elliptic curve group is a cyclic group. Because we've talked about the generator before, and the elliptic curve also uses a generator, right? And the reason why you should understand this concept is that, like, other fields of mathematics use it, like, they assume that you already know it, right? And it's not directly related. They are on their own. It's just like now using mathematics to solve cryptography problems or computer science problems. Mathematics can do without computer science, but computer science cannot do without mathematics, because we basically prove things there and use it in computer science. That's how it works here. If you don't understand cyclic groups, if you don't understand groups, you will not really understand when they start telling you that the elliptic curve group is built over finite field. What is finite field? Finite field is a concept from abstract algebra, which they assume you already know. You understand? But it's a different concept entirely, right? So, I wrote here, an element is said to be generator element if it generates other element. Like I said, W2 is a generator element, W3 is a generator element, right? So we'll just skip this. This is supposed to be another example of cyclic group, but let's just skip this. Now, you have other, like, what we are the what we are most interested in is called finite field, which is the group that which is what elliptic curve uses. But there are many concepts before you get there, so I just listed them here. After the call, I'll share my slide, and I'll also share this note, so you can just go through it. But basically, this diagram basically shows you, um so the deeper you go, the more you can accommodate, right? So basically, groups are stricter than finite field. So basically, groups are telling you that you can only use one operation. But finite field, they're telling you that you can use the four operations. You can use multiplication, you can use addition, you can use subtraction, and you can use multiplication, right? So if you look at this diagram, the more you go, right? So I said here, groups, abelian groups, rings, commutative rings, integral domains, and fields, right? So basically, the deeper you go, the more it can accommodate. So the ones at the top are very strict, while the ones at the bottom are more accommodating, right? So basically, let's just move to finite fields. A finite field, basically, a finite field is basically a set on which the operations of multiplication, addition, subtraction, and division are defined and satisfied under basic rules. Basically, a finite field is a more accommodating version of a group. You understand? So in the group definition, we said that we only allow one operation, right? But finite field, we allow it, it must allow multiplication, addition, subtraction, and division, right? So all these things must hold under this set, right? And I think the best example is a set of value modulo another value, which is what I've talked about before. Like I said, these concepts build on each other, right? So the best example of a finite field is a set of numbers modulo another value, which is like I said, modulo p. when P is a prime number, right? So this is, let's just say, a set of values 0, 1. Okay, let's just, so integers modulo, let's say 7. So basically what this means is the set of 0, 1, 2, 3, 4, 5, 6, and so on. So this is a finite field because 0 0 plus 0, sorry, 0 plus 1 is 1, right? 1 modulo 7 is 1, right? So anything you do here, it will still fall under the same value because you're doing it modulo 7. Even if you do division, division in modular arithmetic is the same thing as multiplicative inverse, which we'll not talk about here. But basically, anything you divide, you will still get the same value under this set. Now, the reason why they always tell you to use prime as the modulus is because if the modulus is not a prime, it will be impossible to get it will be impossible to get division, right? So in mathematics, when it comes to multiplication, addition, and subtraction, they are really basic, right? But when it comes to division, division is a very stubborn operation, right? So basically, that's why they'll tell you that you actually need it to be a prime. If it's not a prime, then you are likely not to get the division, right? So it's only a prime that has a multiplicative inverse. But we're not talking about that one today. So, but basically, the reason why we always talk about prime is because for it to be complete, it needs to have division, and for it to have division, you need to have a multiplicative inverse, and for it to have a multiplicative inverse, it must be a prime number. That's that is by the way. So it's already 7. Ayo, do you think we can go further? Or should I just it's already 7 o'clock now. So.
Right. So I think we can put it to the house. So um yeah, great session. I've actually also gained a lot. But if anybody's happy to drop off now, yeah, cool. If we have people who still wants to, if we could still do an extra 5 7 minutes, if that's fine by everyone, then yes, we can forge ahead. Oh, okay. Already says 30 minutes. Is everybody in support of 30 extra minutes? Like, let the eyes say highs and let the nays say nays. So,
Yeah.
okay, if is in support of
Okay.
30 extra minutes, um, yes. Okay, so I guess the the eyes have it for their chief.
Yeah. All right. Yeah. Nice, nice. So basically, now we have gotten to why we're actually here, right? Which is elliptical cryptography, right? So most of these concepts build up to this particular part, which is elliptical cryptography. So what is ECC? What is elliptic curve? I like calling it ECC so I don't bite my tongue, because yeah. So what is ECC? ECC is basically a curve, right? So like I said at the beginning, the concept of elliptic curve is not tied to cryptography. Basically, cryptography ties to it. You can do your PhD on elliptic curves and decide that you don't want to do anything concerning cryptography, right? So it's not like if you talk about elliptic curve, you're talking about cryptography. No, it's a different thing entirely. People that study curves in mathematics know how they do these things, right? But basically, it has special properties that makes it good for cryptography. That's why we use it in cryptography, right? It has special properties that makes it good, right? So what is what I let it curve? Basically, it's a curve of the form y square equals to s cube plus ax plus b, right? You don't have to understand what that means, right? You don't have to understand what I mean, but basically, it's just if it has this equation, right? Once you see this equation anywhere, you know that it's an elliptic curve. And now, just some caveats, which is like not all elliptic curve can be used for cryptography, right? An elliptic curve must meet some requirements to be able to be used in cryptography. That's why you don't just go around creating your own curves to solve your own cryptographic problems. Cryptographers design, like say, okay, they study many curves and say, okay, you can use this curve to do operations and and um, and you are fine, right? So I think one of the most popular curves used in Web 2 is like P256, which is a curve that was standardized by NIST, NIST of National Institute of blah blah blah. It's a body that are in charge of setting the standard in the United States, I think. Yeah. So basically, there a team that basically say, we have done this, we have done the research for you. You don't need to bother use this curve, right? And if you now come to the Ethereum ecosystem or the blockchain ecosystem, you must have heard of BLS, right? You must have heard of BLS. Sorry, you must have heard of BLS, right? Which is just a curve that was proposed and they now use it, right? So yeah, BLS, yeah. So and the other ones. So basically, you don't just the in as much as they say that elliptic curve are used for cryptography, a curve must meet some requirements to be able to be used for cryptography, right? So, but basically, in a very layman term, this is what once you see this, you just need it's an elliptic curve. Sorry. Sorry about that. So basically, every elliptic curve used in cryptography have domain parameters, right? And these parameters are set by the people that created it, right? So I would have brought in some parameters, but this is a note and it might be too, it might just be too, it will not be nice, right? So, but basically, every elliptic curve used in cryptography has this set of parameters. But before I say that, look at this value here called the special point, which is point at infinity, right? You don't need to think much about it. But now, what this basically means is that there's a point in the elliptic curve known as the point of infinity, which is also the identity element. Now, remember where we talked about identity elements in groups, right? We talked about groups, right? And imagine we've not talked about groups. When you hear identity element, you'd be like, what are you talking about? But now you know that the identity element in any group is that value that once you operate upon that value, you get the same value, right? So basically, if you do point A plus the point at infinity, you should get point A in an elliptic curve because you already know that that's how groups work, right? So any identity element in any group, in anywhere you see it, is that any identity element once operated on by another value in that same set, you should get that same value, right? So that's how elliptic curve work, right? So there's a point called the point at infinity. And also, okay, I didn't actually show that this is how an elliptic curve looks. It looks something like this, right? I didn't draw it, but basically it is symmetric, meaning that this side is equal to this side, right? So this side is equal to this side. I can't get it perfectly, but basically the what you are seeing here will be the same thing as what you are seeing here, right? So that's when it's an elliptic curve, and it's also shaped something like this, right? So it is symmetric, right? And the point at infinity is basically this point, right? So basically, if you draw a line and it's just going up, like it's just straight up, because basically, like if you look at it, it's just going at the top. It doesn't really do anything. So once you get something like this, it is known as the point of infinity, right? So if you do this plus this and you get this, like you get this kind of value, then it's a point at infinity, right? So it is the identity element, right? But okay, now let me now also explain something. We also talk about the inverse, right? Now, I've said that the identity element is that value that once you compute it to another value, you get that same value. But the inverse is that value that once you compute it with each other, you get the identity element. Now, if we have a point P, okay, let me use another ink. We if we have a point, okay, let me use another thing. If we have a point P and we have a point Q and we compute this, right? And we get the identity elements, right? The identity elements, that simply means that Q is the inverse. Now, say as we are relating concept that we have learned before, because now, as me, you didn't know identity element, you didn't know inverse. How would you well, how this things even make sense, right? But we now know that in any group, right? So what groups help us do that? It helps us generalize. You don't even need to know elliptic curves to understand this when people say that, oh, this is the identity element, this is the inverse element, because you know groups, you know finite fields, right? So basically, when you have the identity element, you have the inverse, you know that if P plus Q is the identity element, that means Q is the inverse of P, or P is the inverse of Q, right? So um, that that's why it's very very important to learn these concepts beforehand, so that, because one thing about learning chaotic things is that once you reach the point where you can't link knowledge back, you just become demotivated because you are like lost, right? But when every knowledge links to something back, you're like, okay, because they actually say that the best way to learn something is in the middle of hard and like, if you're learning something that is too hard, you might give up. But if you're in the middle of hard and a bit like you're getting it small, then you can now say, okay, I can move further. But when you're in a point whereby nothing makes sense, then you are likely to give up, right? So that's why it's important to learn this concept beforehand, right? So this is just basically an explanation of how inverse element and relating element works in elliptical cryptography. So let's just quickly go back to something called the domain parameters, right? So every cryptographic construct has domain parameters, right? So it's not just specific to elliptic curve, right? But basically, when NIST, the people that give you a curve and tell you that this curve is good to use, that you go and use it, when they give you a curve, they give you these parameters too. So you can just quickly go online after this call and search P256 curve. You see the values, right? But basically, you have the p value, which is the prime. Remember, we are still going back to what we learned before, which is n. If you remember n, p, the prime. We also use it in finite field here. Here, this 7 is actually the prime. We actually still using it in elliptic curve cryptography, because elliptic curve is under the finite field, right? So we are still using concept from there. So we need p, which is the prime. A and b are constants, right? So if you remember the equation, we have b. These things are constants. They will give you, right? They will give you, right? I think the one for P256 is 7 and 0. So basically you have b is 0 and a is 7. So the equation for in a P256 curve is y squared is equals to s cubed plus 7x. Okay. SC, yeah, thanks. Right. So yeah, this is the values for the curve that Michael posted in the chat, right? So basically they'll give you A, they'll give you B, right? They'll actually give you B, right? So then G is also the generator point. If you remember at the beginning, we talked about generator in the Hellman, which is where you start from. You understand? Where you start from. And these values are not just chosen random. You cannot just choose a set of numbers and choose anything as the generator. It's not possible. You need to test that it's actually a generator, like we're testing for cyclic groups. We're actually testing that, okay, is W a generator, is W square generator. The same thing here, right? So G is a generator. Now you have N. It actually took me a while to understand this N, but basically the time I understand it actually made a lot of sense. The N is basically a the smallest positive integer N, such that Ng equals the identity element. Now, let me explain this using modular arithmetic. When you start doing clock arithmetic, 1 modulo 12 is 1, 2, sorry, 2 modulo 12 is 2, 3 modulo 12 is 3, and so on and so forth. But when you get to 12, it rolls back to 0. That means the order of n, the order of the modulo of 12 is, okay. No. Let's say that we pick a random generator element as 2, right? So basically from 2 to 12, we are counting how many values it takes for the thing to start wrapping around again. If that makes sense. I don't think modulo 12 is the right example, but basically, let's go back to the cyclic group example, which, yeah. So basically, what is the order? What is the order of W? Basically, they're asking you, the order of W is basically how many values can you count before it rolls back to where it started from. That's what the order means, right? And it might not make sense now, but basically when you start computing, you find out that when you reach a particular point, you roll back to the identity element, which is the point at infinity, right? And that value, when you count how many values it took you to get there, that's the order, right? But that's a bit theoretical at this point, so you shouldn't bother much about it. But that's what n means, right? Then lastly h, I don't really see them using much, but basically h is the ratio of the number of points in a curve divided by the order of the curve, and is ideally one, because in most cases, not every time, but in most cases is one, because n divided by the number of points on the curve, like most times the number of points on the curve and the order is the same thing. And if you think about it, it's actually the same thing, because if the generator is the starting element, right? If the generator is the starting element, how many values do you need to count to get back to that element, right? So basically, let's say that 0 is the starting element. How many values do you need to count to come back to 0? It's also the same thing as the number of values in that set. So let's say from 0 to 6 in modulo 7, which we talked about here, 0, 1, 2, 3, 4, 5, 6, right? So if I want to come back to 0, it is 0, 1, 2, 3, 4, 5, 6. It's 7, right? So it's 7, and it's also the same number of values in that set. So basically, 7 is the number in the set, and 7 is the number of values you take to roll around or to wrap around, which is 7 divided by 7 is 1. So in most cases, when you have a generator element and you have the number of points on the curve is also equal to the number of it's also equal to the order. So once you divide it, you get 1. That's why h is ideally 1, but I've not really used it that much, so I feel like it's a bit theoretic, h as a value. Now, we now come to something more specific, which is elliptic curves over finite field, right? Elliptic curve over finite field, which is what elliptic curves are, right? So normally, if you look at this curve, right, you will notice that it's something like this. You have point here, point here, point here, point here, point here, blah blah blah, and stuff like that, right? But because of we are doing finite field, it becomes chaotic, because if, let's say, you have the value 9, and instead of 9 to be here, because of 9 modulo 7 is 2, instead of it to here, it will now go to 2. You understand? So elliptic curve over finite field is not as straightforward as this. It's very chaotic, right? So that's where the hardness of the problems come from, right? And we'll now also find out why it's actually hard, like where you get the strength of elliptic curve, which is elliptic curve's own version of discrete logarithm problem. Because I said before that most of these things are based on hard mathematical problems, and elliptic curve has something called the elliptic curve discrete logarithm problem, which is what the whole idea of elliptic curve is based on, right? And now it's actually shocking to know that the whole hype, or the whole, like, the fact that everybody is saying it's hard, is actually, it will actually boils down to like something, which is a formula being used, and we'll actually get there, right? But except you want to just use it on a shallow level, if you want to go deeper, you have to understand this concept. But at the end, you just find out that it's just some formulas that you have to understand to be able to use it, and then you can now build up from there, right? So yeah, a set of points where 0 raised to less than or equal to xy less than p. This basically means something modulo p, right? This basically means, so any value on that curve must be modulo p. So even if you get 2000, you must do it modulo p. If p is 7, 2000 modulo 7. So you must wrap around that value. So that's what this thing means. It's not that, is that what it means? It's not higher than that. So basically, we talked about the equation above, and this is just the same equation, but modulo p. So now we are operating on that curve. We're operating on a finite field, so we need to do modulo p. If it's not modulo p, then it's not on the curve. So any implementation of elliptic curve you see, or any implementation of, yeah, if you actually check, I'll add resources to my slide, and you find out that in my implementation of elliptic curve, you find out a function called is on curve. So any value you get, you must check that it's on that curve, because not all values are on the curve, right? So there are a set of values that are on the curve, because if it is not modulo p, it's not on the curve, right? Because you can't put in 9 into a set of value is modulo 7. 9 is not part of it. You have to wrap it around to get 2. You understand? So that's how these things work. And okay, this short example just explains the idea of having something on the curve, which is basically if I want to know the amount of values in a curve, I just put in I just put in these values one by one. I put in 0 modulo. Okay, so I have the y value, I have the x value. So basically, if I want to check if it's on the curve, I would do the right hand side modulo p equals to the equal to the left hand side. If it's equal, that means it's on that curve, right? So this equation assumes that we already know the value of y. You get? So basically, anything you're doing left hand side equal to right hand side. If it's on that curve, then you can say it's on that curve. I'll actually send a link to a visualization of an elliptic curve that will help you make sense of these things. But it actually be on the resources part of the slides. But basically, this we can basically test if something is on the curve by testing each value inside of this equation, right? Now, let's just see an example. We have an elliptic curve modulo 17, right? And we have 19 points, right? We have a generator 5, 1. Because remember, this is a curve. 5, 1 means that it's a point. If you remember linear equation, a point on a curve or a point on a two-dimensional plane is xy. So you have the x value, you have the y value, and you plot it, right? So that's why you have 5, y. So if you remember, we are now working on a on a two on a two-dimensional plane, not on a number line anymore, right? So we have points instead of single values. That's why you are seeing fm 5, 1, because g is a point on a curve, not a normal value. You understand? So g generator, and you do 1g, you do 2g, you do 3g. So what 1g means is basically g itself. What 2g means is g plus g. What 3g means is g plus g plus g. As you all know, multiplication is simply repeated addition, right? So basically that's what we are doing here. We are doing repeated addition, right? And there are algorithms to complete these things faster. So you don't necessarily start doing, if you want to do let's say 1000 you now start doing g plus g plus g. No, it's very inefficient. There's an algorithm called double and add algorithm that is used to compute this thing, and this is the whole concept of this is actually where the hardness comes from, right? We'll actually talk about that. This is where the hardness comes from. Basically, what it means is that giving a equals to ng on an elliptic curve, right? If I just give you a and you know, if I give you a and you know g, I'm telling you it is close to impossible to get n. It is close to impossible. In fact, right now, right, the reason why we are still using elliptic curve in blockchain and everything is because it's impossible to find n. So when you say private key and public key, your private key is this n, right? Your private key is n, and a is your public key. It is impossible to get n. It has not been proven to get n. Yes, for smaller bit size, like I said at the beginning, the security of a cryptographic algorithm is tied to the bit size, which is the number of values. Because if you say that you want to do elliptic curve and you're using modulo 17 like me, yeah, anybody can crack it using guesswork, sir. But most of these values are very huge that you can't even start. It will take you millions of years to even compute it in a very fast computer, right? So the whole idea of elliptical cryptography is the fact that if I give you a and I give you g, it's impossible to get n. That is the whole gist of elliptical cryptography. That is elliptical cryptography equivalent of discrete log problem. So this thing basically is the elliptic curve discrete log problem. This thing you're seeing here, this problem you're seeing here now is elliptic open version of the discrete log problem. And this is much harder to solve than the first one. The first one is modular arithmetic. It is hard to solve, but with a smaller bit size, you can find it. But for the same bit size in elliptical cryptography, it is harder to solve. Like I told you before, the reason why most people use elliptical cryptography is that you can achieve the same amount of security with a smaller bit size, right? So for you to achieve the same security you can achieve in elliptic curve, you need like times 30 bit size, right? You need like times 30. If you're using 256 for ECC, if you want to achieve the same amount of security using normal discrete log problem, you probably need to use like 256 times 30. And you know that once you start using high bit size, you're using a computer, your computer have limited resources. You understand? It doesn't make sense to start using huge values, right? So this is the whole gist of elliptical blah blah blah. Right now, one thing you need to understand is how do you get these values. So when I say you should solve for 2G, how do you go about it? Right? You know, we talked about 2G here, right? 2G here, you understand? 2G, 3G. So basically, lastly, I want to just show you the formulas you need, right? You can actually get these things online, but no, let me leave this one here. Yeah. So basically, how do you compute 1G, 2G, 3G, 4G, and 5G, right? So we just use basic information. We just use this information. You have a point P, you have a point P, you have a point Q, right? And they say find P plus Q. Or if it's the same value, they say if you find P plus P, which is like 2P, they have a different formula, right? So what you do is that you first find the slope, you understand? And their conditions, right? If the values are different, you use this formula. If the values are the same, you use this formula. Then when you find S, which is the slope, right? S is the slope, then you just bring it here, right? So if they say P plus Q, you do slope raised to power 2 minus x1 minus x2 modulo P. You do to find the second point, which is the y point, you do S times x1 minus x3, which is one you got here. You know, x3, you got it here, minus y1 modulo P. This is the formula. So you don't even need to, if you like, you don't even need to be like if you want to understand why these things work, you can go further. But this thing right now is the whole gist of elliptical cryptography, which is how do you basically you cannot find these values, right? So when you now want to do something like 4G is repeated addition, right? So you just do this plus this plus this plus this, right? And like I said, there's an algorithm called um it's called double and add algorithm. Double and add algorithm, which is an efficient algorithm for finding um 2G, 3G, 4G, 5G, right? So let me just recall a bit, right? If I give you A, which is the public key, and I give you G. In fact, I don't need to give you its public. G is generator, everybody knows generator for any popular call. And I compute NG equals to A. It is impossible, or right now it is impossible to get A. Sorry, it's impossible to get N because N is my private key, right? And because of how hard it is to find, that's where the whole security comes from. Any elliptic curve, no matter how complex it is, it still boils down to what is their what is their formula for point addition? What is their formula for point doubling? How do I compute AG? Sorry, 1G, 2G, 3G, 4G, that's all. Even if you check BLS, BLS is a more complex curve and it has a slightly different formula for solving point addition, right? But at the end, it is still how do I find age 1G, 2G, 3G, 4G, 5G, and so on and so forth, right? So um as in every field you have this is the most basic, right? But you might hear something like projectile coordinates, Jacobian coordinates, blah blah blah. Basically these things are just variations of what the thing is actually talking about, right? So that's why if you just jump into a paper now on elliptic curve, you get lost because many things are foreign to you. But once you know the basic, you actually you might not get immediately, obviously, but after a while, everything starts to make sense to you, right? So last but not the least, let's do P plus Q, right? So when we do this, we just end and we'll call it a day, right? So we have P is equals to 5 1, Q is equals to 6 raised to power 6 comma 3, and we have this curve. If you notice, I told you that A and B are constant, and in this particular scenario, this is A, and this is B, and this is P. 17 is the modulus, right? So how do we solve this? Basically, we just go to our formula, right? So let me just quickly copy this formula and bring it down. So basically, let's just keep our formula somewhere here. Let's just keep our formula here. And now, how do you solve it, right? So let's first find the slope. Since there are different values, we just do y minus y1, x2 minus x2, and so on and so forth, right? So this is x1, this is y1, this is x2, this is y2, right? So how do we find the slope? We do s equals to y2 minus y1 over x2 minus x1, and don't forget modulo p. But funny enough, if you don't do modulo p here, but you do modulo p here, you will still get it because modulus is associative, right? So even if you don't do it now, if you do it later, it will still work. But for the sake of correctness and for the sake of understanding, let's just do it like this, right? In fact, this is how you should do it, right? Basically. So y2 is 3, y1 is 1, x2 is 6, and x1 is 5, right? So 3 minus 2, 3 minus 1 is 2, 6 minus 1 is 5, is 1, 1 modulo 17 is 1. So our slope is is 1, right? So how do we get the new point? So remember, we are solving p plus q, right? We are solving p plus q. So we already know s. So let's find x3. X3 is equals to s is equals to 1. So 1 square minus x1 is 5 minus x2 is 6, right? So if you do this, basically 1 minus 5. So this is, I think, 1 square minus 5 is minus 4. Minus 4 minus 6 is minus 10. Yeah, minus 10 modulo 17. Now, if you know, modular arithmetic seems easy at the beginning, but until you start the negative value. So let's see how to solve this, right? So basically, minus 10 modulo 17 is basically what is the closest number, what is the closest number, the smallest number to minus 10 that will give you, that will be divisible by 17, which is minus 17, right? So when you do minus 17, now when you do 17, um so when you get 17 as the nearest value, you now do minus 10 minus 17, right? Seems I'm not getting this. Minus 10 minus 17 is okay. I think I'm actually getting it. Minus 10 minus 17 is, oh, I actually got this wrong. Let me just consult my Minoga and do quickly. Oh, I've gone to clean what I'm not supposed to clean now. 1 minus 5 minus 6 minus 4 minus 6 minus 10 modulo 17. So minus 10 modulo 17 is 7. Thank you. Yeah, it's 7. Okay, now let me actually show you how they actually solve this. This is a bit unrelated, but in case you find this anywhere, what they did is 17. Like I said, the closest number to minus 10 that will give you, that is divisible by 17, is minus 17, right? So what you do is that you do minus 10 minus 17. I think this was where I was missing it, right? So what this now gives is minus 10 plus 17. You now have a positive number, right? Minus 10 plus 17 is 7. So this is how modular arithmetic works with negative numbers. You find the closest number to that number in the negative that gives you that number, right? So minus 17 divided by 17 is minus 1, right? So that's why you have this value. So when you now minus it, you get 7. So that's how they got 7. So let's go back to what we're saying. So now we have y3, right? Um, y3. The formula is s into okay, let me just use s as it is. 1 into x1 is 5 plus, so minus x3 is 7, gotten 7, right? And minus y1. Y1 is where's y1? Y1 is 1, right? So 5 minus 7 is minus 7. 5 minus 7 is minus 7, yes. 1 times minus 1. Oh, what am I saying? 1 times minus 2 is minus 2, right? Minus 2 minus 7 is minus 3. Minus 3 mod 17. If you remember the first, what we did at first, the closest number to 3 minus 3 that is divisible by 17 is 17. Minus 3 minus 17. Minus 3 minus 17 is minus 3 plus 17, and minus 3 plus 17 is 14. So we have we have P plus Q is equals to 7 comma 14. So this is the point on the elliptic curve when you compute um, P plus Q. And ladies and gentlemen, we have come back. We have come to an end. We have come to the end of this session. I urge you to try out this P plus P, which is 2P. So just use this. Just use this formula here. Just use this. The only difference is that you now use this one as a slope. You understand? You now use this one as a slope, right? So yeah, we have come to the end of this session. Mike, Ayo.
Yes, thanks and Gospa for yeah, very educative, practical session. Um, Even as somebody who has not delved into it before, I mean, I was still able to follow through, and yeah, at least the very basics. And I am positive that it was a profitable session for everyone who joined and for everyone who is even still on the call. We shot past the call time by like 36 minutes, but it was worth it. Um, we for the rest of this month, we still have other programs that would communicate on within the community. For example, there are plans underway to bring some folks from Ethereum to come for a protocol session, and there's still a ton of event stuff that the community port and the event port and the tech port of the community is planning for the entire house. But yeah, would get some extra updates within the group. I don't know if Chibi wanted to share anything. And the call is recorded, so after we drop off, I'm going to leave the recording on within the community in case we need to fall back on the call just for reference. Chibi, I don't know if there's anything, Chibi, if there's anything you'd like to um, add.
Uh, yeah, I have something. Thank you, Ayo. Big up to you, Godspa. It has been very, very fun to. So, my question would be like, so what's next? Like, what? Because one of the ideas behind this was like, this was going to be sort of like a building block to for people, and they can go off and and do stuff. So, like, what would you suggest as the next step to? Is it like contributing to stuff? Like, how would you, for someone just like, how would you say they should go off on this?
Yeah. It's a very, very good question because these things seem abstract. So looking for where to apply it really makes a lot of sense. So one thing I found out about learning things like this is that you need to have like a mindset shift kind of, which is basically that you can learn them, right? Because they seem hard. Like I always saw elliptical cryptography as rocket science for a very long time. I saw it like something I cannot learn. I saw it like something that is just for a few group of people that are really, really, really smart. But like I said, or I've been saying during the call, like chaotic things are just chaotic, right? Because there are many moving parts, and when you don't know those moving parts, everything seems like everything working against you. Because once you enter anything, they start telling you things you don't know. You just feel like, oh, let me go and do the ones I understand, right? So first of all, one thing I want everybody to get from this call is that the framing behind learning this kind of thing is breaking them down into smaller parts. You understand? And they are hard, right? But if you break them into smaller parts, the probability of you being demotivated is lower. But if you just, let's say you jump into elliptical cryptography straight up from the top, you are likely to get demotivated because if you don't know it, you don't know it. It's as simple as that, right? So the best way I think we can apply this is to spend more time learning about it, right? And in terms of application, look for look for maybe projects, right? Like let's say open source projects that need this kind of things, right? Or even just on your own, right? Like one of the ways I learned this was during Ethereum Protocol Fellowship. I started this thing where I was just implementing cryptographic protocols, and that was what helped me understand these things. Because when I was doing them, I was trying to write educative comments on the code, and as I was writing the code, I was like, when you write, like writing makes you think better, right? So when you write, you say, okay, does this thing make sense? And before you know, you start learning just to make your writing better, blah blah blah. You've understood it in a better ground, right? So basically, depart from understanding it to being able to use it somewhere. It is subjective. You might just see an open source project tomorrow and you can contribute to it, right? But if you want to grow on your own without looking for the next open source project, you can just start implementing these things yourself, learning more about it, learning why I said that prime numbers are good for modulus, learning why um some curves are not good for elliptical cryptography, blah blah blah, right? So these things are boring concepts, right? So the line between use understanding this thing I just said in this call to using them in real life, it depends on you. But I would say that the long-term benefit is really a lot. So you can spend your time understanding this concept, whether you use it in a protocol or not, like just spend some time understanding. Before you know it, you're able to gain knowledge that you can apply out there. So I don't know if I answered your question, but this is why I think about things like this.
Yeah, you did. You did. So like just contributing to projects or just keep learning on your own till you find.
Yeah,
Thank you very much.
yeah.
Okay, so I mean, like, thanks, Gospel. Thanks everyone for joining. And just to add to what Gospel said, I feel like it's just the way I think of every kind of learning. It's introductory conversations like this are like the parent rock from where like you can build whatever it is you want to build. Like that's why I'm always very, very particular about who introduces me first to a particular subject matter. I think this has been solid, to this particular discourse, and whatever it is you build on it from, whatever it is you build upon that foundational knowledge, then it's really up to individuals. But one thing I'm also going to propose, I think, in the event community and event board is that we have this technical deep dives in series, right? So I feel like there should be it's reasonable if after a couple of weeks, if we set up something like this and everybody gets some to-dos, right? You say, okay, take the next 1 2 weeks and find this and do, right? Do this and this in next 1 week, next 2 weeks. Then we'll do some kind of check-in, let's say, 2 weeks after, or in the following month to say, okay, what did we get to do? I feel like that way we're able to create a learning journey. So it's not like the last time we had a deep dive, we just picked account abstraction, we did it and we dumped it, and now we've jumped onto something else. So I feel like if we have a learning roadmap, if we, let me rephrase, if we're introducing this process like this or learning modules like this, and we create a learning roadmap around it, it's very easy to track and grow communally, and people can say, okay, from the last time we were together, I actually went to learn about this and I found out this, and if it's okay to share. So we kind of have a mix of a continuous learning roadmap and a knowledge sharing session. So the design around it, yeah, I'll probably share that with the community pod so we can think around how feasible that can work. But it makes our approach to learning these things more productive. So yeah, that's the only thing I just thought to add very quickly.
Yeah, yeah. I also want to quickly add that I would be doing these kind of things. Um, like I'll doing these kind of things throughout the year. So at any point in time when I want to do them, like I would share on the on Leaders Connect, so you can like register and stuff like that. But yeah, um, yeah,
Okay, great. I mean, that's very useful. Please, like, where if you have
yeah,
like a kind of calendar schedule, I think we can use to follow through. Then that would be great. That would be very very useful. Thanks, Gospar. Thanks, Chibi, for setting this up and giving us access to have this insightful discussion, elliptic cryptography. We're going to send in the information for the remaining events for the month, and since we've already opened the year with our Aguero moment of multiple fundings within the community, like hopefully we keep doing amazing stuff, keep building good stuff, and keep getting rewarded. Thank you guys for joining. Thank you for your time, and I hope you have a productive week ahead. Bye.